twice, which means that the p-value for this fit would be 30.8%. Okay, what else can we learn from the fit? This is my last slide. So we do have the best fit parameters, but as I said, we also have a very good sampling around the best fit parameters. So we can also evaluate the area of the parameter space that is still in good agreement, though not quite as good as the best fit point. And from this area, we can derive mass spectra like this. So this shows in red the masses at the best fit point for all the superpartners. In dark blue, the range of the masses of the superpartners that are still allowed within the 68% confidence level. And in light blue, the masses of the superpartners that are still allowed within the 95% confidence level. And then we can use these predictions to calculate other observables and find out, for instance, where in the second run of the LHC a search for supersymmetry might be most promising. So this is everything I have. Here's a summary. Try to show you in the beginning that we have quite a lot of different supersymmetry models with different levels of complexity. So the most complex one that we talked about was the MSSM, 124 parameters, and the PMSSM with 24 or 18 parameters. CMSSM will have 4 parameters. I try to give an overview of all the tools that we have to calculate masses and decays and cross-sections. Gave you an overview of the observables that we can use to constrain supersymmetry models. And in the final part, I try to show how we combine all the information that we have to infer something about the given super model and maybe exclude the model. So that's
Thank you very much.
If you want to read more, a small collection of the papers.
How did you calculate this, the key square? Did you use any tool as statistical, for instance, or it's a code you have to?
Yeah, that is actually, that's the Fitino code. Fitino is a software package, and in Fitino all these algorithms to jump around in the phase space are defined and implemented, and then Fitino calls external programs like Swing or Softsuzy to do all the calculations. And then in the final step, Fitino grabs all the information from the external codes that it needs, and then Fitino calculates the question.
Yeah, but this the other analysis when you calculate the mean y square, then you plot that the other in the next yes, this plot. Then it does makes all this calculation.
Yes. So this plot would basically be one of the outputs of Fitino. And in addition, we have to each of the points that enters this histogram in the output, we have the corresponding values of the parameters and also the corresponding predictions of the given model. Yeah. It can be quite frustrating to use it because you have to compile and build all the external codes, and then you have to set up the interface. So if you really want to try it, maybe you can.
Because I used to calculate Suzy in Maghreb, but and I have to perform codes all by myself, and that's good. It's very bad. If Fitino makes for me,
yeah, you can try it. I can't promise that it will really work out. You can try it.
But this Fitino is not just working for the constrained MSSM, and it can work for whatever model you have, or for the others.
In principle, yes.
For CMS constrained.
Yes. So we are currently at the stage of recoding the whole thing. So let's say give us 1 year or maybe 1 year and a half, and then you should be able to take any model you want.
I see.
And put it into Fitino. Just define the model via an input file, and Fitino will take care of the rest. Maybe you will have to write your own calculator for that model. You can interface it with Fitino, and Fitino can do the sampling of the model. At the moment, you can only use the models that are built in Fitino itself, like PMSSM, CMSSM, GMSP, AMSP. That's probably it. We have some more fancier models, but I'm not quite sure. So usually, just due to the small number of parameters in the past, the only thing that you could do technically was fitting the CMSSM as 4 parameters. We also have tried this with 24 parameters, but it takes, just to give you an impression, usually it takes about 1 second, maybe 2 seconds with additional codes to calculate all the observables for a given point in the CMSSM parameters. And you want to sample a very large part of the parameter space, you have to sample a lot of points. So usually for our last result we had 100 million points that we calculated, roughly 100 to 200 million points. So it took us very roughly 200 million seconds to do all the calculations, which is quite a bit. And if you add more parameters, you have to calculate more points. The number of points that you have to sample grows exponentially with the number of parameters. So one additional parameter, the number of points that you have to calculate explodes. This is one of the technical problems.
May I ask a question? Maybe it's very formative for our beginners, for the students. Sometimes most of the people here, they are used to discussion with theoreticians. So theoreticians have, let us say, well-grounded motivations to believe that Susie could be a good physicist beyond the standard model. But I mean, for you as an experimentalist, I know that you are just finished your PhD, but I believe that you have a lot of thoughts about that. As an experimentalist, how could you convince some people that Susie is maybe a good physicist beyond the standard? I mean, as a theoretician, it's very easy.
Yes.
They have very good motivations. I mean, not philosophical, really first principle motivation. But as an experimentalist, I mean, how would you support in favor of Susie? I know that, but I mean, it's a forum here, very democratic forum. I mean, just for thoughts, you can read, no problem.
I guess the reasons for experimentalists to think that Susie is a good candidate for physics beyond the standard model are essentially the same as the ones from the theorists, just maybe seen from a different angle. So for me, one of the most convincing arguments that Susie is a good extensionist. It predicts dark matter, and in addition to predicting dark matter, it solves quite a lot of the shortcomings of the standard model. It's just one modification, and I don't want to say all the problems, but a lot of problems that the standard model has are solved right away. And other extensions to the standard model can typically not do that. So you have extensions which solve 1 or 2 problems of the standard model, but the other problems remain. And maybe you get even more problems, you add problems. So Susie is, well, at least according to my knowledge, one of the few, if not the only, candidates for extensions that really solves all the problems. Right? Theoretically, there are also problems with supersymmetry, like the fine-tuning issue. If we don't find supersymmetry soon, that would mean that the masses of the superpartners are very large, and that is once again theoretically unappealing. A view that I don't share and don't understand. But that's a good discussion.
Okay, people, if you want to have more questions, I think Matthias is available. Okay, anyhow, he's staying here. Matthias, where are you sitting here at SBTF? Which floor? Which room?
610.
610. So people feel free, especially the students, feel free to come here at Matthias to ask questions, okay? And he's here just to share and maybe to help us, to defend the supersymmetry at SBTF. Supersymmetry has been under attack in many places, but especially here. Supersymmetry is many people hate it here. So So maybe it's a good time to have a good, to form an army to defend Susie at CGTF. Thank you so much indeed. You came here as a warrior. Thank you so much.
If we are looking for people